Great. As Ahmad said, my name is David Zage. I am from Intel, and I am the time architecture lead. As many of you probably know, my mentor and former manager, Kevin Stanton, has retired, and so I am taking over as the architecture lead for time at Intel. And this is actually supposed to be a joint presentation with two others. As you can see on the slide, Seth Friedman unfortunately could not be here and had to be actually in New York today. And as I mentioned earlier, Kevin has actually retired. But in the kind of continuing on the vein here, we're going to look at delivering precision time, and in particular, kind of a little bit of a focus on delivering time in financial services. So quick outline. I won't belabor the point, but we'll kind of look at where precision time has come from. I know we've had a few people talk to that, and so we won't do too much. Why it matters, how it works, and the kind of the first mile, the last centimeters, and the call to action. Oops, sorry about that. So, kind of, I think an interesting and important piece, and that kind of goes into why it's important, especially in the financial services, is kind of a little bit of evolution of time and computing. When we just had our own servers on our desktop, or our own computers on our desktop, even just laptops, typically we weren't really that much needed for synchronized time, and for any applications we typically ignored time or didn't trust it. It's only when we really started to get into having kind of distributed systems, and in particular trying to correlate events, especially kind of if we are looking at how do we analyze when something failed, or when we have events that we need to know how they correlate, then we actually started to need to deploy services like NTP and actually have time synchronization, at least at a higher level here in the hundreds of milliseconds type of range. And it's not really until we really start to get to coordinated computing where we really need to have higher precision time and time accuracy. It's when we're starting to actually have events that need to be able to occur in relationship to each other, have a full ordering to those events, that we really need to start to deploy P2P. And then, I think in the future here, we will see that the evolution of this will continue, in that we will have in the future another line there down below that which will probably start to actually travel into the picosecond realm itself. So why does precision time matter? I think we've already been talking about several different domains, but just in case, there's kind of two cases where the first is that you need time synchronization both to help you meet your own deadlines, but also that you have the time synchronization itself as required. So as mentioned, you have some of these functional safety pieces like automobiles, you have industrial, you have video conferencing, you also have your AR and VR. I know if people have been wandering around the exhibition booth out there, you probably have seen the headsets. If you want your augmented reality to function well, to actually be able to mirror reality, you need time-sensitive networking, and you need precision time for that. If you go and you actually turn some of it off, you can oftentimes have your augmented reality wander away from where you're at in your virtual world. And then finally, you have things like mobile robots and those type of things. And then on the bottom half of the slide, we have some of the pieces that's more about the time synchronization is required. Typically, the deadlines aren't quite as important in this case, but it's more about what is the timeline of events, what is the causality of events that are actually occurring. We have 5G, and in particular here, the one I highlighted here is the financial services. I think many people in the room are aware of this, so I won't belabor it too much. But this is kind of looking at how do we get precision time into our system, into our servers. The first step is we actually. Those are backwards, great. But the first step is we actually have IEEE 1588 P2P to actually do synchronization to an external source. We are able to use the packet-based protocol to distribute the phase and the frequency and be able to synchronize to our network reference clock. And then the The second piece that we can also use heavily, especially when you have things like regulations that you need to double check and verify, is the output of your time general purpose output or your TGPIO pins in order to determine that, yes, my accuracy of my clocks and my synchronization is actually what I think it is. And being able to measure that my system time versus a PDP capable source is what I think it is, and it's unaffected by the system load itself. And I think it was actually covered really nicely in a few of the previous presentations of how do we get time from some source down to our actual server. And here I call it the first 45,000 miles, in that we have it come from some type of atomic clock. It goes up and down our GNS or basically our satellite receivers to a grandmaster in the network. The grandmaster does that calculation, and it finally passes this along to our target system, and the target system is able to use that. It comes through our NIC, and that NIC is resident on a device, and then the host itself is actually finally able to use that. And so the last piece that I think is also very important is the last centimeters. So how do we actually make sure that that time that we brought in with tens of nanoseconds of accuracy actually is usable by our system software with also tens of nanoseconds of accuracy. So here on that slide, you can see in the top half, we have the CPU there in gray, and on the bottom half in the weird kind of beige orange color, we actually have the NIC. And so we're actually able to use PTM, which is part of the PCIe standard. And so we're able to actually do multiple communication rounds. And here you can kind of ignore the first one. That's kind of almost like I call priming the pump and getting the communication ready. And then how do we actually look at, if we're at time T2, how do we get the current time of the time in the NIC versus the time in the system. And so if you look here on the slide, you can see we basically need to determine what the time is on the NIC as well as what the time is on the CPU. And we do that using the fact that we can calculate the link delay. And this is also assuming that the link delay is symmetric between T1 and T2 and T3 and T4. But using this piece, we can now have a accurate synchronized timestamp of the PDP root time and the actual PDP counter, and then be able to use this to discipline whatever clocks we need to in the system. So that's all great in the fact that that's kind of the theory of P2P or PTM. So we've gone from having time all the way in our atomic clock, came to our systems across our data center. It has now gone into our systems. It is now available at the system time. And so, one of the things is, how great is it? Well, you can actually see here that, kind of the air bands around that are in the, tens of nanoseconds, so 30 to 30 or so. And then as we actually have a cooled system, you can see that that actually improves the accuracy of the timestamps. Shouldn't be too surprising. As we've heard earlier, temperature does impact things and does matter. So this is just a really interesting result, but it's also something that shouldn't be too surprising to the folks in the room. Another piece that's great is that PTM is unaffected by the CPU load. Here you can see that depending on the load from 0 to 75, basically, all of those pyramids look the same, or I guess they're inverted pyramids, but they all look the same as they should in the fact that, PCIe PTM is designed to be a hardware path that runs over the PCIe channel, and so this avoids the need or the influences of CPU as well as congestion on things like your buses and fabric. I'm sure Seth would have some other very cool things to say about this, so definitely happy to follow up more with folks if there are questions. But kind of going to the what's next. So this was talking about PTM. We were talking about nanoseconds of accuracy. Obviously, one of the next things, especially in some of the high financial trading pieces, is the more accurate you are, the better your systems are, the more money that you can make. And so this is, we're looking towards, can we go towards picosecond accuracy, start to look at how do we do White Rabbit on some of the FPGA and standardized hardware that LMS Systems is actually working with. How do we synchronize to accuracies better than 1 nanosecond? And so this kind of brings us to the call to action, in that, and I think if anyone here has talked to Ahmad a bit, you've probably heard him say, we want to treat the data center as a PC. And so this is actually moving us towards that direction. Let's deploy infrastructures that support precision time measurement. Let's look at where we can deploy White Rabbit, and let's start to think about what it means if we can do picosecond. What type of applications does that enable? What type of benefits does it have? So I will go there to thank you. And are there any questions?
All right, questions. Nobu.
Well, hi.
Oh.
Thanks a lot for your talk, and I'm glad to see somebody's work doing this, continuing this work at Intel. And my question is about the temperature difference, and it's, in some sense, it's not surprising, but it's also surprising because it's doing the sort of hardware time stamping, and so when it's hot, what is sort of adding the noise? Is it a path length or some component that behaves strange?
It's actually a really great question, and that's actually something we hadn't dug in a little bit further. We think it's actually part of the fabric, but we're not sure.
Okay, thank you. You have another question.
Did you have another question? Oh, sorry. It's hard to see you guys out there with those lights are ridiculously bright.
That's on purpose, I guess.
Right.
So I'm confused about your inverted pyramids. Each of those showed that you've got your same kind of synchronization error is different at different parts of the stack. We're a software company that uses SmartNICs, and we're always communicating with the host processor and the FPGA logic. And so we're aware of a lot more uncertainties that happen when you go over the PCIe bus or the CXL bus now, as it is right now. Mm-hmm. So how do you account for the buffering and the queuing delays on the PCIe bus in your assumptions of your measurement?
Well, I mean, I guess part of it is the fact that we are using the. Well, I guess there's two pieces. Is the queuing delays and the buffering delays. Since we are doing PTM is not. It needs to be timely, but it doesn't have time bounds on it. So if it takes longer to get to us, we still know the accuracy of that snapshot. So that snapshot isn't impacted by the fact that it might take a few seconds longer to get it back to us or not. So I think that's part of the reason we have the snapshot. And the second piece is the fact that I completely lost it apparently. Sorry.
We'll talk later.
Yeah, please. Thank you.